Okay, so we are gonna keep on going with our cultural conditions and cultural requirements of plants, and we're going to be talking about the requirement of water. So we've talked so far about water, nutrients. So, sorry, we're going to talk about water today. Um, we've talked about nutrients, soil, climate, and so now we're diving into water. So obviously, plants need water. Okay. If there is a native planting or a naturally occurring planting, those plants are adapted to the climatic conditions that they are in, and therefore they're also adapted to the amount of water that they receive naturally. So we've talked about Mediterranean plants, and there's California natives in in their own respective independent regions within California in their own climatic areas. They, once they're established, if they're in a planted landscape, they don't need water, supplemental water at that point. If a plant is not in its natural location, if it's used in a landscape and it is not a native to that region, then it will typically need supplemental water to get established, as well as to continue to live and thrive. So how do we do that? Of course, we do it with irrigation. So we're going to go through irrigation systems. We're going to go through irrigation terminology, hydrozoning. We're going to look at California water issues, soil water plant relationships, and irrigation system scheduling, which is kind of a that one can tend to be a bit of a mystery for people. There is a really defined way to address irrigation scheduling, but it is sort of an area and a career all on its own. So what I'd like you to do is click on this link. Obviously, you're going to have to, I have the link posted within the same place that you found the link to this lecture. So you can click on it there, or if you have the slide deck open as a PDF, you can click on this link. It is a irrigation system overview, about a 20-minute video done by Hunter, who is a irrigation manufacturer. They actually have amazing products. There's lots of manufacturers out there. I don't have a preference for Hunter or Rainbird or Irritrol or Toro or any of the companies. My opinion is whatever the best product is for the situation that you're dealing with, that is the one that you should use. So anyways, but Hunter does have great videos on irrigation. So click on this link. It's a 20-minute video to walk you through the general system components of an irrigation system in the landscape. And once you've watched that, come back to this video. So pause this video, come back to this video, and we will dive into irrigation terminology. Okay, welcome back. So you learned about the basics of an irrigation system, valves, mainline, point of connection, or I guess point of connection, mainline, backflow prevention device, mainline. Sometimes there's a meter or a master valve, and then valves, lateral lines, sprinklers. Okay, so that's the basics of an irrigation system and the basic components. There is a irrigation class that is taught at ARC, Hort 110. It's irrigation design. And in that class, we really get into the nuts and bolts of irrigation systems, and it's a whole semester only on irrigation. So if you're interested in this subject, hopefully you will enjoy this this sort of lightweight irrigation overview for Hort 300, Intro to Horticulture. But if you are, again, if you're interested in diving deeper into irrigation, which is a really excellent spot to be career-wise, especially right now and over the next 100 years. So if you're interested in diving deeper, that's a great class to take. But we're going to go through some stuff that wasn't reviewed in the video that you just watched. So we're going to dive just a little bit deeper. So basics of sprinkler systems and basic terminology. So basic terminology includes radius. Okay, so if we're talking about sprinkler systems, pop-up sprinkler systems, rotor sprinkler systems, basic terminology and general things that need to be known. First one is radius, and that is the distance that the water travels from the sprinkler out. Okay, so if this is a top view look at the wetting pattern, that a sprinkler that would be in the middle of this semicircle, then the radius of that sprinkler or rotor is the distance that the water is thrown from the sprinkler itself to the outermost portion of that circle that it creates. Okay, so radius. Arc is the degrees of coverage of a sprinkler from one side of a pattern to the other. So a 180-degree arc would be half a circle pattern. So right here, if there was a sprinkler right in the middle of the semicircle, then the arc of this one would be 180. This is 180 degrees, or simply called half. Obviously, there's increments below and above, and they do go smaller than this. So they can go down to 45 or even very, very narrow throws or very narrow arcs, all the way up to 360. So when you're talking about sprinklers, you're looking at the distance that it throws from the sprinkler being radius, and then the wetting pattern of that circle being the arc of the sprinkler. So really important when it comes to sprinklers, and this is another term that we really need to know and be familiar with and understand, is head-to-head coverage. So sprinkler spacing and nozzles should be selected so that the radius of throw, remember the radius of throw, provides coverage from one sprinkler to the next to provide the most uniform coverage. Okay, so these sprinklers are putting out a certain amount of water. Okay, so this is in plan view, and here we have an example of head-to-head coverage. This sprinkler is spraying to this sprinkler, and this sprinkler is spraying back to this sprinkler. And it's not just one-to-one. You can see this in a square layout here, that every single sprinkler throws a radius of water to the next 2 or 3 or 4 adjacent sprinklers. So they all overlap. Okay. The reason that this needs to be done is that in sprinkler systems, you can see this as a wetting pattern, right? So if we look at a cross section, a vertical wetting pattern in the soil, if this is this sprinkler, its wetting pattern is that there's more water that falls closer to the sprinkler than falls further away from the sprinkler. So in order to get as uniform as possible coverage, we need to have each sprinkler spraying back to the next adjacent sprinklers. Now, rotors are a little bit different. rotors have a bit of the opposite wetting pattern. So if I flipped this and this, brought this one to here. So again, this is the yellow wetting pattern. And this is the purple wetting pattern. Okay. So with that, rotors throw more water further away from the sprinkler itself. And so you need the same head-to-head coverage, right? So this one here, it's the yellow wetting pattern, less water falls adjacent to it and more falls further away from it. And so in order to achieve as uniform a wetting pattern as possible, we still need that head-to-head coverage. You can see in this example that we don't have head-to-head coverage. The wetting pattern just hits the adjacent outside edge of the adjacent wetting pattern. So in this case, you don't end up with uniform coverage. You end up with much more water here, very little water here. This is not the proper way to lay out a sprinkler system. Funny thing is I found this graphic on some blog of some DIYer that put this together to show people how to put sprinkler systems together. And it is 100% incorrect. So be careful out there if you're, doing some internet searches for how to do things. Make sure that whoever's putting it together knows what they're talking about. So head-to-head coverage, incredibly important. And I have had on job sites with inexperienced contractors that are building my projects. I have not gotten into arguments, but I have been argued with on my designs for people trying to convince me that this is the way that you lay out a sprinkler system, and it is not. So head-to-head coverage, very important term. Now, with this head-to-head coverage, there's a couple ways to achieve it. There's square spacing and there's triangular spacing. So square spacing is typically what we see on, typically we see it on smaller areas, okay? And they can be really large areas. We see this installed in large lawns. The triangular spacing, you can see that it's just a little bit more efficient. Okay, so in the square spacing, you see that you've got these overlap patterns here, right? So you have this overlap here, but this right here, this from this head, this sprinkler, it's throwing 300, the arc is 360 degrees. It's actually hitting 4 other sprinklers, but it's not getting close to this sprinkler, okay? Just because of the square spacing. Sprinklers throw circular arcs, circular pattern, and so it can't make it all the way out to here. If you switch to triangular spacing, you actually get much closer. So you get more uniform coverage, and so it's used in really large areas. But once you get close to any kind of straight line, you end up with a bit of an awkward wetting pattern, right? Because you'd need a sprinkler here, but it would, the overspray would be a little bit awkward. So in really large areas, parks, golf courses, etc., you see a triangular spacing a lot, very rarely in residential settings of normal size. Sometimes there's huge residential projects with giant lawns, and it could be used in that case. So with square spacing, you get less overspray. Reason being is that you can stop it adjacent to walkways or any kind of straight line. With triangular spacing, inevitably, if you have some sort of barrier, walkway, driveway, etc., adjacent to it, there's going to be some overspray on it. you get a little bit lower application rate of um, um, water. You get the downside is the coverage can be impacted by the wind. Sprinklers can always be impacted by the wind. With triangular spacing, you get that tighter spacing with more overlap. So you get sort of more uniform coverage. It's a little bit higher application rate of water. It is actually a better approach to use in windy conditions, although any time you shoot water through the air and there's wind, then the pattern gets disruptive. And again, the overlap typically results in overspray. So the next term that's really important to understand is precipitation rate. Precipitation rate, okay? Often referred to as PR, or precip rate, or application rate. Okay, but in this instance and in general, we're going to reference it as precipitation rate. Now, what it is precipitation rate is the amount of water applied over a period of time. With sprinklers or any irrigation, it's measured in inches per hour. Okay. It's very important to understand precipitation rate because we use it to create irrigation schedules. We need to understand it so we can avoid runoff in heavy soils or clay soils. When we're talking about sprinklers, typically fixed spray sprinklers have much higher precipitation rates than rotors, and we will go into a couple examples of that. Okay. Now, this right here is an irrigation chart. Okay, so this shows an irrigation chart for a rotor, so a type of sprinkler, and this is telling us which nozzle is used on that sprinkler. Okay, so it tells us that with a certain pressure, at that sprinkler, so pressure of water at that sprinkler, it will throw a certain radius, the flow through that will be a certain gallons per minute. And therefore, with square spacing, we would have a certain precipitation rate in inches per hour. And with triangular spacing, remember there's a little bit higher application rate, we would have a certain precipitation rate. Okay, so in this case, at 45 pounds per square inch, so 45 is the pressure of water at that sprinkler, it should throw 31 feet. It will have a flow of 1.5 gallons per minute. And it, with square coverage, square spacing, it will have a 0.3 inch per hour precipitation rate. So if we relate that to rain, right? Precipitation. In California in general, if in a 24-hour period, if we get 1 inch of rain, it's raining pretty hard, right? It's a pretty like heavy precipitation rate. You can visually see that. So if you relate that to a sprinkler, that's what sprinklers are replicating. And this is a pretty high precipitation rate, right? If we compare it to what we think of as a heavy rain or downpours. So in that, with this sprinkler on, in that 24-hour period, if we did 0.3 inches, we multiply that by 24, that's equivalent to 7.2 inches in a 24-hour period. Okay, so precipitation rate is really important to understand because we need to know how much water that system is putting onto the ground or into the ground. Lots of times people, well, the really common question is, how much do I irrigate? Right? I get this question a lot. What should I set my system to? How do I schedule my irrigation system? The answer is it depends. Okay, it depends on a ton of different factors that we'll get into in a couple minutes. Okay, but this is a very important one. You have to know the precipitation rate of a system in order to accurately replace the amount of water that the plant has lost through transpiration, right? Remember, we've talked about transpiration. Transpiration is measurable. We'll get into how transpiration is measured. You also have to replace the amount of water that is lost from the soil through evaporation. Okay. And so the way that we need, the really key factor in that is understanding the precipitation rate. So when we're looking at precipitation rates, right, and remember here we had avoiding runoff in heavy soils. This is a really important one. We've talked about soils. We've talked about sandy soils and how they can have really high infiltration rates, right? Water flows through it very quickly. And clay soils, it holds on to water. It can hold a ton of water. Okay? And so water flows through that very slowly. So we need to take that into account when we're looking at our precipitation rates, right, of our sprinkler systems and the type of soil that we actually are irrigating. So this right here, actually, I mean, this shows source of Hunter Industries. I think that this is originally from USDA, but really doesn't matter. So if we look at the soil type, and in a coarse sand soil under flat conditions with either cover or being bare, and the cover could be with mulch down, or bare could be bare soil. So the cover can be with mulch down, or there's ground cover, etc. So in those conditions, the coarse sand can take 2 inches per hour, okay, which is pretty high. As we move through loams and down into heavy soils, heavy clays or clay loams, it can take water much slower. Okay, so if we are using a number 3 nozzle with triangular spacing, we would be putting down 0.46 inches per hour. But on a flat slope in clay soil, with coverage, whether that's mulch or ground cover, etc., it can absorb water. Water can infiltrate into that soil at only 0.2 inches per hour. So at some point, if you're irrigating with a number 3 nozzle, that soil will become saturated and will run off. Okay, so that water, once that soil is saturated, it will start to puddle and it will start to go off of the intended irrigated area. Okay, so understanding our precipitation rate and understanding our soils is very important when we're selecting which systems to use, which precipitation rates we're putting down. So pressure affects nozzle performance. Okay, pressure affects all sorts of, well, pressure affects all irrigation systems. Okay, so the pressure impacts the sprinkler flow rate and the radius of that sprinkler, and so it also affects the precipitation rate. When we're looking at these nozzle charts, and you can find these in any irrigation catalog, it will show us a range of pressures because as water moves through a system, um, pressure is reduced. Okay, and if you're interested in this kind of information, again, Hort 110 irrigation design is a great class to take for it. So we won't get into this really deeply, but if you're looking at these nozzle charts, it's important to understand that if there's a lower pressure, generally the radius is shorter, the flow is less, and therefore the precipitation rate is less. When you're looking at these nozzle charts, generally the mid-range, okay, the mid-range of the given range is the optimal for that particular nozzle or sprinkler or whatever it is you're looking at. In this case, they've highlighted it. Okay, so the range is 25 to 65 and the mid-range is 45. They've highlighted it, and this is the optimal operating pressure for that nozzle on that sprinkler. Okay. The range is given, and so with this given range at 25 to 65, you should never be under a condition where the operating pressure at that sprinkler is lower than 25 or higher than 65. Okay, you lose uniformity, you lose a lot of stuff that was designed into the sprinkler if you go below or above that range. But optimal range is the middle of whatever the range is given on the chart, or the optimal pressure is the middle of that range. With rotor systems, the landscape irrigation systems are designed, if they're designed well, they're designed to achieve a certain pressure at the furthest sprinkler. The way that you can measure that, right? Things are designed, things are built, and then there's the reality of it. Now, measuring that at that sprinkler, if you're using rotors, you can use pitot tube, so a pressure gauge with a pitot tube, and you literally shove that pitot tube right into the flow. And that will give you a reading of what the pressure is at that sprinkler itself. With pop-up sprinklers, there's different things that you can do to actually measure it right at the head to see what the likely precipitation rate is. Okay, so again, we're just hitting this lightly, but I want to give you guys an overview of sort of the technicalities of irrigation systems. So on from precipitation rate to matched precipitation. Okay, matched precipitation is very, very important. Matched precipitation ensures that all irrigation zones have matched precipitation that are uniformly watered. With sprinklers, check the manufacturer's specifications to ensure nozzles are matched. Inline drip or line source or grids. So we'll go into some drip system stuff. So same thing, use manufacturer's specs to ensure matched precipitation, and use a sprinkler audit to determine where different nozzles need to be used. So matched precipitation, we're going to get into this in this diagram here, or these pictures. So these are different types of nozzles, okay? The sprinkler body itself is essentially from this pop-up portion to this portion and the body that's below ground. The magic there's a lot of great stuff that's incorporated into the bodies, but the precipitation rate of this nozzle, the amount of water that comes out of it in a given period of time is really of this whole setup here is really in the nozzle. So with fixed spray, and this one right here is considered a fixed spray, it's a 180-degree arc, and it throws out a fan of water. The precipitation rate is 1.8 inches per hour. That is true if you're using a 180-degree fixed spray or a 90-degree fixed spray or a 360 degree fixed spray. So if we zip on back to our coverage here, we see that if there's a 90-degree fixed spray with head-to-head coverage, each one of these is putting out 1.8 inches per hour. So with combined, right, with the head-to-head coverage, you get 1.8 inches per hour in the entire area, as long as you have head-to-head coverage and you're using all fixed sprays. And so it would be putting out 1.8 inches per hour. This nozzle here is called the MP rotator, and you've probably seen these. It looks like little individual streams of water that kind of like fly through the air. These are actually really good nozzles. Same thing with, but it's 0.41 inches per hour, right? So if we zip on back to this and we look at that 1.8, right? That would work under light sandy loam soil, but not necessarily under clay soil. You're going to get runoff pretty quickly with that 1.8 inches of water per hour with the fixed spray system. But the MP rotator, right, 0.41, it puts water down much slower. Now, with the MP rotator, the arc is variable. Okay, so you can have a 45-degree arc. That's actually kind of a weird one, but you can have a 90-degree arc, 100-degree arc. You can adjust that. It's not fixed, but it's still match precipitation. So no matter what the arc is set to with MP rotators, it's going to be, as long as you're using uniform spacing, so square spacing layout or triangular spacing layout, you're going to be putting down 0.41 inches per hour. I'm sorry, that's in square spacing. With triangular spacing, your application rate is going to be a little bit higher because there's more overlap. So, but you do have a match precipitation. Okay, Toro Precision nozzles, these are fixed, but it's a pretty technical nozzle. This is a really good nozzle as well. It has a low precipitation rate, much lower than the fixed spray, but it does have a match precipitation rate. Rainbird R-Van nozzles. Rainbird R-Van nozzles, very similar to the MP rotator, a little bit higher precipitation rate than the MP rotator, but match precipitation nonetheless. Rainbird HE vans, same thing. It is match precipitation, but it's a little bit higher precipitation. Okay, but these are variable arc nozzles as well. Now we get down into other types of systems that throw water through the air: micro sprays, shrubblers, bubblers, rotors, and van nozzles. Now, these ones on the bottom, none of them are match precipitation. None of these are match precipitation. So if you have, we'll just skip the micro spray, shrubler, bubblers. Bubblers are good for tree establishment, but you don't know, water basically flows with gravity and then with soil. So you don't know what the precipitation rate is, so it's very difficult to schedule it. Shrubblers, dangerous. You can see the range in precipitation rates in that, 10 to 20 inches per hour. Micro sprays, same thing, range of precipitation from 2 to 4 inches per hour. And I'm gonna actually change this right now. So that was wrong, sorry about that. Rotors, now rotors, technically, they are not match precipitation. They are really good for large areas because their radius is typically very far, right? They can throw from 10 to 70 feet. Okay, so depending on what rotor you're using, what type of pressure you're working with, they can typically throw from 10 to 70 feet, which is great for really large areas. But you need to nozzle it correctly or you need to zone it correctly in order to achieve match precipitation. Okay, so it is possible to come close with rotor systems, really close to match precipitation, but they need to be designed correctly. Rainbird van nozzles, these are really dangerous nozzles. They're very inexpensive, they're super flexible, and people like to use them because they're very inexpensive. Give you an example, these are about $1.75, whereas the MP rotators are about $8 each. Okay, so especially DIYers, homeowners, etc., they typically lean towards grabbing these nozzles because they're so flexible, because the arc, you can change it from essentially 0 degrees up to 360 degrees. But the real challenge is that there's no match precipitation. So a 8-foot radius with 180-degree arc might be putting down 3 inches per hour of water, whereas the next sprinkler may have a 15-degree radius with a 180-degree arc, and that might be putting down 1 inch per hour of water. And so with that, you don't get uniform coverage. You do not get a uniform precipitation rate. You do not get a matched precipitation rate. Therefore, it's very difficult to schedule and efficiently irrigate that area. Okay, so key terms: radius, arc, square spacing, triangular spacing, head-to-head coverage, precipitation rate, and match precipitation. So with sprinkler systems, there are definitely some obstacles. Irrigation runoff is a significant obstacle. So the excess water from an irrigation system that flows off the surface and into storm drains or into any unintended area. So irrigation runoff, this is 100% waste right here. And when it's going over roads or asphalt or concrete like this, it can end up being expensive damage that happens to this. Overspray is water that lands beyond the planted or irrigated area. When overspray lands on sidewalks, drives, or other hard surfaces, it can and does empty into the streets and local waterways. So both of these are not desirable whatsoever. Okay, these are typical issues associated with sprinkler systems, with systems that we throw water through the air to land in a desired area. But things aren't perfect, and so typically we have runoff and overspray. Now, low volume systems, drip systems. Drip systems is a type of micro irrigation system that has the potential to save water by allowing water to drip slowly to the roots of plants, either from above the soil surface or buried below the system, below the surface. So in this case, you see we have an emitter that's on a poly tube, a drip line, okay? And this emitter acts like the nozzle. You select this emitter for the gallons per hour that it puts out, okay? This one here, this one's called a point source system. This one's called an inline system. This one has built-in emitters, and we're gonna go through each one. So drip systems reduce overwatering. They avoid irrigation runoff. They apply water directly to the root zone. They minimize evaporation, and they can be line source or point source. So the difference, and you guys saw some of this in the video from Hunter, this is sort of the system that they go through, right? We've got a meter, a point of connection, a shutoff valve, a backflow prevention device, sometimes a pressure regulator if needed, a master valve, a valve, and in this case, it's going to a rotor system. So main line to valve becomes lateral line to a pop-up rotor, all the same from the same valve. In this case, It is a pop-up sprinkler system with MP rotators. This right here is the drip system. Okay? And it's important to understand that with drip systems, we need a couple extra components. They're lower volume and lower pressure, and so we need to reduce the pressure downstream of the valve and have a filter, because the emission device that the water is actually going through, those are very small orifices. So anything that comes through this mainline system, any grit, any debris, etc., and it does, right? If you've ever lost pressure or flow in like the bathroom or the kitchen sink faucet and unscrewed the nozzle on it, you can see built up stuff in there, right? Sometimes it's hard water buildup, but a lot of times there's just broken up debris in there. Water, stuff like that comes through our systems all the time, and it comes through our irrigation systems as well. With rotors and sprinklers, typically there's an extra filter within that, but the orifice is a little bit larger, and so a lot of times that debris can come out. With drip systems, the orifice is very small, and so we need to make sure that nothing gets into that to clog up any of those emitters. So the really key difference in the actual system itself is that it has a pressure reducer and a filter. So our point source drip systems, they're good for sparsely planted areas. So if you have a great distance between plants, it's good for that. It's very flexible. The challenges to it, though, are that there's lots of parts, and so lots of parts that can break. And it's very difficult to determine an actual precipitation rate, because each one of the emitters is putting out a certain gallons per hour in the area that it's dripping onto. But it's very difficult to put this system together and then to be able to say this system puts down 1 inch of water per hour, okay, because of the high flexibility in the system, and that you can stick emitters anywhere, okay? Now, they're good systems, but again, the downfall to them are that there's lots of parts that can break, and it's very difficult to determine an actual precipitation rate. So scheduling it becomes very difficult. Now, I put these pictures here, and you can see the actual layout. This is polytube. This is a 1/2 inch line, goes to 1/4 inch line, and then goes to the emitter. These are the pictures that you typically see in big box home improvement stores. Okay, we all know them, Home Depot and Lowe's. And it's very misleading. Okay? I sort of think that they need to take these off of their pictures in their marketing material. You never put a system together like this. So first off, you see that this 1/4 inch tube comes off of the 1/2 inch line at an angle. You never want to do that, because if somebody steps on that, it's going to break. And you see this sort of popped up here and water dripping off, same thing. You do not want this above grade. I think that they do this so that you can see how the system's put together, but this is the wrong way to do it. You need this drip line under the mulch. You need the 1/4 inch coming off of it parallel to the ground surface, and then these should be installed again under the mulch and not popped up at all. This is sort of a disaster waiting to happen. Now, other type of drip is an inline drip system. These are really good for all landscapes. You can use these on lawn as subsurface, as you can see this in the diagram here. They are highly flexible. There's very few parts, and it's very easy to determine a precipitation rate. Okay, so here, instead of an emitter going, or multiple emitters going to each plant itself, you uniformly irrigate the area with drip emitters that are built in at a certain inches on center, and the rows spaced at a certain inches on center. And what determines that is the type of soil. Right, so if we pop back to this, right, this here in a heavy clay soil, you would have further row spacing and further emitter spacing so that you have a lower precipitation rate. With sandier soils, you'd have rows that are closer together and emitters that are closer together and higher flow rates because that soil can take the higher flow rate without saturation and runoff. Already went through all that. Perfect. So here you can see in this diagram, so there's charts that you can follow here. So if you know the soil type you're working with and what you're actually irrigating, lawn or shrubs, ground covers, etc., and the type of soil, it will tell you if you're irrigating shrubs and ground cover at grade, in a clay soil, you should use a 0.26 gallon per hour emitter inline tubing. The spacing on the emitters should be 18 inches. The row spacing should be 18 inches. And therefore, your precipitation rate or application rate would be 0.19 inches per hour. And if we relate that back to our heavy clay soils, that 0.19 is a pretty good spot to be, right? Get back to normal here. Now, so there's charts for this, right? And you can see that using inline drip systems, you can get to a known condition. There's this calculator. Okay. Click on this. This is the link. I'm just going to bring it up. It brings you to Netafim's Techline calculator. Netafim is another irrigation manufacturer. If you go to calculate, okay, so you please do this. You can go through certain conditions. So let's say that I have a on-surface system for shrubs or ground cover. I'm in a loam soil. My pressure, remember we have a pressure regulator. My inlet pressure is 30 PSI. 30 PSI. My square footage is 500 square feet. Go ahead and just keep the tech line check valve. Okay, it's a certain type of, it's a certain product that they make. It's kind of the best one. What it does here when you put in all these conditions is it gives you the flow rate of the system that you need to use. Okay, it gives the flow rate. So the emitter is each emitter puts down 0.42 gallons per hour. It's recommending that our emitter spacing that we select is 18 inches on center, recommended at 18 inches on center. It's recommending that our row spacing is at 18 inches on center. So if we zip this back to here, so that would be our emitter spacing at 18 inches on center. So you can see that there, that there. So it'd be 18 inches on center. So along this line here, every 18 inches, there would be an emitter. The row spacing, so one drip line, next drip line. So the installed row spacing would be at 18 inches. And it tells us what the application rate is, what the precipitation rate is, 0.3 inches per hour. And it's telling us that the acceptable precipitation rate for that soil type, we decided it was a loam soil. Okay, so we can see that this matches up with our precip rates, and we'll zip back onto this so we can look at what that is. All right, so our loam soil is 1.5 to 1 inches per hour that it can take. And what this is putting out is 0.3. Okay, and it's telling us that the range is a little bit lower than that USDA thing, but you can see the correlation there. You can get this product in 100-foot coils, 250-foot coils, 500-foot coils, 1,000-foot coils, and then it's telling us some other stuff which you guys don't need to be that concerned with right now. The other nice thing that it does tell us is that the time to apply a 1/4 inch of water is 50 minutes. The other thing that it tells us by going through this is through that system, what the flow rate is. Okay, so going through that lateral line to the first emitter is going to be 1.55 gallons per minute. Okay, now that's an important thing to know for irrigation design, because then you can determine what the pressure losses are. But again, you really need to take the irrigation design class to really understand what that means. But there are these calculators out here for this sort of thing. So this is how you use them. And this right here is the link to get there. Now, irrigation audits, it was mentioned earlier, an irrigation audit is used to collect and provide information about a current and planned irrigation system operation and overall condition of the system. So by design, these systems operate in a certain way. In reality, they're always a little bit different. So we use irrigation audits to figure out what actual precipitation rates are. Okay. This is a picture of somebody doing a catch can test where you lay out a bunch of, they're called catch cans. This is what they look like. And they run the system for a certain period of time. They measure the amount of water that falls into the catch cans, do some calculations, and from our irrigation charts, right, it tells us, yeah, it should be about 0.48 inches per hour, right, under these conditions. But again, the reality of it is it's going to be a little bit different. So irrigation audits are very, very helpful to be able to figure out exactly what the uniformity of the system is and the precipitation rate is. So these include a visual inspection, an evaluation of the distribution uniformity, so how well that system performs. So if it's not perfect head-to-head coverage and not matched precipitation rate, then the distribution uniformity is going to be really low. It's going to be poor distribution uniformity. With the irrigation audit, this is one of the most important things, the actual precipitation rate. You can also determine the landscape's watering needs. We'll go into that. And then we use it to review and develop an irrigation schedule. Biannual audits are recommended, and with some projects, some landscapes, it is required. And it is a requirement for a certified landscape for certain projects to get final inspection. There are projects that require an irrigation audit. Now, the audits need to be conducted in a manner consistent with Irrigation Association Landscape Irrigation Auditor Certification Program or another US EPA WaterSense labeled auditing program. QUEL is one of those, Qualified Water Efficient Landscaper. These are programs and exams that you can take to become a certified landscape irrigation auditor. This is a great certification to have. I do irrigation audits frequently, and it's actually and they're going to be required more and more. So if you're interested in this, look into these programs, but also understand that that Hort 110, the irrigation design class, really helps to gear you towards that and understand it. So the things we're trying to figure out is with an irrigation audit is the distribution uniformity. This is a measure of how uniformly water is applied to the area being watered. It actually expresses a ratio or a decimal to avoid confusing it with efficiency. Okay? And again, Hort 110, we'll get more in depth on this stuff, but typically it's expressed as 0.81 or 0.75. as opposed to 75% or 81%, et cetera. The precipitation rate, we've gone through this, right? But this irrigation audit is really what it, how you determine the actual precipitation rate. The manufacturer charts are helpful to get close, but in reality, you need an irrigation audit to truly determine your precipitation rate. You can get close otherwise, but not exact. On to hydrozoning. So hydrozoning is the practice of grouping together plants with similar watering requirements in an effort to conserve water. Grouping plants into hydrozones is an approach to irrigation and garden design where plants with similar water needs are grouped together. Okay, so this is a plan view of a landscape. This shows us that there are moderate water use plants, right? The green ones, these are all moderate water use, moderate water use. The low water use are the blue. And then there's some very low water use plants and a little couple zones. These are probably raised beds that are high water use. Okay, now with hydrozoning, it's important to group plants with the same water needs into the same areas. That way you can irrigate them to what they need under that same valve. So you really take this hydrozone, right? This would be a hydrozone. This right here would be a hydrozone. This right here would be a hydrozone. And you develop a valve zone. Okay, so this number 5 zone covers this area. These are all low water use plants, so they need a certain amount of water. These moderate water use plants are zoned together in zone 4 and 3, and they need a certain amount of water. The reason that this zone 4 and zone 3 are irrigated separately is because they're under separate sun exposures. Okay, so a moderate water use plant under full sun is going to have higher is going to have higher water needs because it's in full sun. Those same plants in part shade would need less water because they're going to transpire slowly and there's going to be less evaporation. Okay, so you separate these because ultimately this is going to need longer run times or more applied water than this. Okay, and these are isolated into hydrozones. If we mix these, right, if we have high water use plants with low water use plants, then, and we have a certain irrigation system, then we're going to end up over irrigating our low water use plants in order to provide enough water to the high water use plants that that are in that same area irrigated by the same system. Okay, so hydrozoning is very important. The way that we do this is by grouping the same plant water use characteristics with similar and isolating different solar exposure zones. This right here is the actual irrigation design for this. So you see we have red main line going to valves, going to lateral lines, and then irrigating the areas. Factors to consider when you're hydrozoning: the slope, sun or wind exposure, plants in ground versus pots. It's very bad to irrigate pots and in-ground plants at the same time on the same system because plants in pots lose water faster than plants that are in the ground. Considering the water needs of the plant, the soil type, new versus existing plantings, and available zones on the controller. Now, in my opinion, I would replace the controller. If you're limited on the number of zones on the controller, replace the controller to get more zones. On to California. Okay, and water issues in California. If we look at water in California, okay, overall, we have this as a pie chart breakdown. So I'm going to zoom in on that a little bit. Oops. So if we look at this, it's kind of interesting. We have different water uses for all the water that is capturable in California. We see that there's almost a 50-50 split here, right? If we look at this line. Above the line, we have water that is reserved and allowed to flow for wild and scenic rivers, in-stream flows, required delta outflow, and managed wetlands. This is all environmental use. This is what's needed to keep California flowing. Okay. This is considered environmental use. It can be a little bit controversial. There's a lot of people that think, oh, well, why do we need water to keep flowing through our rivers? Well, it's really important, especially when we're considering the delta. If we don't allow water to outflow through the delta, then salt water comes in and will drastically change the habitats. Okay. You need environmental water. So 50% of the capturable water in California goes to the environment through managed wetlands, outflow, in-stream flows, and wild and scenic rivers. The other 50% goes to irrigated agriculture and urban water use. Okay, so 41% goes to agriculture, 10% goes to urban water use. Now, if we dive into what urban water use is, there's residential indoor water use and residential outdoor water use. Large landscapes, commercial, industrial, institutional. Of course, there's always losses, and then there's some other, right? But if we look at this pie chart, a significant portion of it, a hugely significant portion of it, goes to landscape, right? So of this urban 10%, a significant portion goes to landscapes. And if we look at residential, right, 50% of the of water goes to residential indoor use, 50% goes to residential outdoor water use. That's a pretty good split right there, a pretty accurate split. That being said, we have water issues in California. Okay, there's not enough water for the amount of people. So we need to be very efficient with our outdoor water use, because ultimately we still have to drink water and we still have to shower and wash dishes and clothes, etc. That's not going anywhere. We can get more efficient with that. But in the outdoor, it's very important that we're very efficient with our irrigation. This is just a breakdown of sort of where California's urban water goes. Okay. A third of all California water goes to urban landscapes. A little less than 2% of all of California's energy goes to treating, moving water to urban landscapes. So this right here this shows, various water uses throughout the different regions of California. But one thing that is really important is that to understand is that water use in California is also, so there's also energy that's needed in order to get that water to our systems. Okay, so electricity is used for that. Carbon emissions are put out in order to do that. Projected climate change impacts in California, average by 2100, average annual maximum daily temperatures are projected to increase by 5.6 to 8.8 degrees. By 2100, our water supply from snowpack is projected to decline by 2/3. Okay, so very important to ready ourselves for this and to be working with incredibly efficient irrigation systems. Water conservation is equivalent to energy conservation. So 19% of California electrical energy is used for water. 16% of this energy is for urban water conveyance and treatment of water. This doesn't include heating water, in-building distribution, or wastewater treatment. So 1.15% of California electrical energy is attributed to landscape water use. So really, water conservation is energy conservation. It's really important to make that connection. So when my teenager is trying to warm up the water in the shower and he's just letting it flow before he gets in, I used to say you're wasting water. Now I say you're wasting water and energy. Okay, very important to make that connection. So now we're getting into soil and plant water needs. Basic relationships between soil, water, and plants. There's spaces between those soil particles. We've talked about that. They contain water, which moves upward through plants. That water cools the plants as it evaporates off the leaves and other tissues. That water carries essential nutrients into the plants and helps maintain cell size, right? Turgidity, so that plants don't wilt. Water serves as a raw material for photosynthesis, the process by which plants capture light, energy, and store it in sugars for later use. Okay, we've talked about that, but plants need water. Now, we can do things to improve our soils. We've talked about that, and improve the amount of water that's available or storable in those soils. A robust living soil with sufficient organic content is the foundation of a water-conserving landscape. 1 cubic foot of soil holds roughly 1 quart of water for each 1% of organic matter. Remember, as we increase organic matter in soils, our water holding capacities go up. The frequency and duration of irrigation water required for a landscape varies significantly with soil type and organic matter content. You can see in this graphic here that a clay soil at 1% organic matter holds 50 gallons of water. Okay, I think this is, yes, per cubic yard of soil. As we increase our percent organic matter, the water holding capacities significantly increase. Okay, so organic content in soil, increasing that percentage increases the water holding capacity and the ability of that soil to store water. Deciding when, so this helps us to decide when to irrigate. Okay, plants withdraw, this is important to understand. Plants withdraw soil moisture to meet their evapotranspiration demands based on weather conditions, okay, and the plant traits. So plants will constantly pull water out of the soil. That's how they stay up and alive. And as water is depleted from soils, it becomes more and more difficult for those plants to withdraw water from that soil. Soils that can store larger amounts of plant available water do not need to be irrigated as frequently as soils that store smaller amounts. In general, sandier soils need to be irrigated more frequently than soils with a greater clay content that are heavier textured. A given plant will use water at the same rate regardless of soil texture, but it will run out of water sooner in a sandier textured soil. So that statement right there, it's important to understand. If you have a plant that can handle being in clay soil or sandy soil, they will use water at the same rate. But in the sandier soil, it'll run out of water faster. This is that same graphic. How quickly a soil can absorb water will help to determine what kind of irrigation to set up. So understanding your soil is a very important aspect of selecting and designing and installing an irrigation system, because you need to understand what the precipitation rate is, and using high precipitation rates in sandy soils is acceptable. High precipitation rates in clay soils is very challenging. And this is why. Okay, soil type will determine how to set up the irrigation systems. This chart is based on using drip emitters and establishing proper spacing. So the wetting pattern in clay soil that wetting pattern goes far out away from those emitters and down very slowly. Sandier soils, on the other hand, water spreads out in a narrow column but goes deep quickly. And so that's just a graphic example of that. On to irrigation scheduling. So the concept, an irrigation schedule should determine the duration or the runtime, how long the system will run for, and the frequency, how often that system should irrigate. The variable components that we need to understand are weather, the plant water use, the system uniformity, and the application rate. So we're going to go through how to determine the weather factor and how to determine the plant use factor. We've already talked about the system uniformity that can be determined through an irrigation audit. And essentially, it just says like, how good is your system? How efficient is it? How uniform does it put water down? And then that system application rate is the precipitation rate. Okay, so we've already talked about these two things. We're going to go into the weather and the plant water use. The weather portion. The way that the weather is addressed in terms of irrigation scheduling is called evapotranspiration. Evapotranspiration. Evapotranspiration, also referred to as ET, evapotranspiration, is the process of transferring moisture from the earth into the atmosphere. Evaporation occurs when water vapor leaves soils or plant surface. So evaporation, when water leaves the soil as water vapor. And if there's water on plants, it can evaporate off of the surface. Transpiration involves the passage of water through the plant, right? We've talked about that. That happens during photosynthesis. The combination of those two things is called evapotranspiration. And when we're irrigating, that is what we are replacing as it relates to that plant water use. But we need to know what the evapotranspiration rate is in order to understand how much water we need to replace via irrigation. So this is the weather variable that helps us to quantify the amount of effective irrigation that a plant will need within a given period of time. It's measured just like the precipitation rate in inches per unit of time, inches per day, inches per week, inches per month, inches per year. And you can figure it out to the inches per hour if you want, but that's a little bit too nitty gritty. The way that we figure this out is through the CIMMYS program. California has a statewide system of computer-operated weather stations that generate what is known as real-time evapotranspiration, the reference evapotranspiration rate. And this is a link to that. When you go on to it, this is what it looks like. So you can go to stations. And I like to go to station location map. And I like to zoom in. Here's the one that is closest to us. Station 131 is Fair Oaks. Now I can go into data. And I can drill down to station 131, select it. I'm going to select a limited monthly report. And I'm going to run that report. And we can see that in June of 2023, the evapotranspiration rate was 6.94 inches in June. 6.94 inches in June. So if we relate that, 30 days in June, so 6.94 inches in June divided by 30 days, that's 0.23 inches of water lost through evapotranspiration per day in a high water use crop. Okay? In a high water use crop. Here, this one was same thing. This one was a different station. This one was at Point San Pedro. In July of 2022, 6.32 inches were lost. There's 31 days in July. 6.32 divided by 31 gives us 0.2 inches per day. 0.2 inches per day times 7 is 1.4 inches per week. And that's for a reference evapotranspiration rate of 100%. Okay. So the way that they actually do this is they put a CIMA station. So let's dive into that. Just go back here. Our CIMA stations look like this. Okay, they take a station, they take a bunch of sensors and they put it on a 400 square foot area in full sun with very healthy, well irrigated, high water use lawn. And in that location, they measure how much water vapor is coming off of that. And that sets the 100% mark, right? So it tells us how much water is coming off of that in full sun on a high water use plant area and kept in really good condition. So that sets the bar for what a high water use area needs in terms of replacement irrigation water. Now, that's for high water use plants. What do we do for other plants? Well, we go to WUCLs. WUCL stands for Water Use Classification of Landscape Species. Here, we go into WUCLs and we looked up a certain type of plant, Ceanothus Ray Hartman. And we see that this is Ray Hartman. Most Ceanothuses are low water use. And so it's 10 to 30% of reference evapotranspiration. So if we relate this back to this condition, where in a high water use area, we need to put down 0.2 inches per day, right? On the lawn in full sun, in whatever region you're in, you got to put down the appropriate amount of replacement water. So in this case, it was 0.2 inches per day. Well, with a low water use plant, it would be so the 0.2 inches of water per day. If we only do 20% of that, we would be putting down 0.04 inches of water per day. Okay. Now, the way that we determine that, again, is to go into WUCLs. So I'm going to dive into WUCLs for you. And we click on Plant Search Database. We select a city, Sacramento. Let's select a plant and let's do Chondropetalum tectorum. Chondropetalum tectorum is a low water use plant, so it would need 10 to 30% of reference evapotranspiration per day. This is how we conserve water. This is how we schedule irrigation. This is the plant factor of our irrigation schedule. Okay, so this is how you do that, and it's it's very helpful information. If we dive into this a little bit, you can see that there's different regions. Okay, now there's different regions because evapotranspiration rates are different in different regions. So North Central Coast is going to have a lower evapotranspiration rate than the Central Valley. You can see here that South Inland, essentially like the Imperial Valley, this same plant has a moderate water use. It's going to use more water in that region. Okay, so region by region, We have certain plants that use more or less water. For other plants, so our hydrangea macrophylla, our big leaf hydrangea. On the north central coast, the water use classification is moderate, but the Central Valley, it's high because it's hotter in the Central Valley. Okay? So very important to make that connection. Now, again, take Hort 110 irrigation design to really dive deeply into this, but there's apps for everything. Here's a couple links. So this link will take you to Water Wonk, and the nice thing is lawn month is July. ET water weekly, 1.4 inches of water. The plant factor, it is lawn, so the plant factor is going to be high. It's going to be 0.9. Our precipitation rate, let's say we're using MP rotators. So our precipitation rate is assumed to be 0.41 inches per hour. Our distribution uniformity, again, to figure that out, you really need to do an irrigation audit, but let's just say that it's a sprinkler system. So typically those sprinkler systems uniformity is about 0.75, if that. Click calculate. Runtime per week is 245 minutes. We take that 245 minutes, we divide it by 7. It needs to run for 35 minutes every single day. Now, on that same site, maybe we have low water planting. July. ET rate's the same, right? It's the weather. That doesn't change. But our plant factor based on WUCLs and our hydro zoning is 0.2. The precipitation rate, let's say that we're using NetFM. And so our precipitation rate is 0.3 inches per hour, which is pretty similar to the 0.3. Well, let's actually just say that we're irrigating with MP rotators as well, which you actually shouldn't do, but just for equal comparison. And our distribution uniformity is the same. Click calculate, right? So same location, different plant factor, same precipitation rate, same distribution uniformity. This only needs to run for 54 minutes per week, right? So we don't need to run that for 35 minutes a day. We run that for 7-8 minutes per day. Okay? So that's how you conserve water in landscapes. And this stuff all 100% available to you and free. CIMUS, figure out what the weather factor is. WUCLs, figure out what the plant factor is. So all that being said, irrigation, especially, it always has been a great area of horticulture to go into, but especially now and literally for as time moves on, hundreds of years, right? Well beyond our lifetime, the irrigation industry portion of horticulture is going nowhere, and there's going to be more and more jobs. There's very few people that effectively go into this. You can become an irrigation designer, an irrigation contractor, an irrigation technician, irrigation manager, irrigation auditor. There's a lot of money to be made in career through irrigation. Okay. So if you are the type of person that loves plants, loves horticulture, and you have a decent mind for math and some technical aspects, this is a great area of horticulture to go into. So that's it. plant cultural conditions, water, we replace it with irrigation, and it's a very important aspect of horticulture.